Good afternoon, everyone. I'm very glad to welcome all of you to AI Lab seminar today. And this topic today is called tumor detections based on medical images using deep learning. Firstly, I will introduce a little bit about myself. I'm Long VD3, and now I'm doing internal communications for AI Lab. And AI Lab is a virtual lab focused on AI research and training activities founded by Mr. Nguyễn Xuân Phong, Chief AI Officer since September uh, 2019. And everyone who is knowledgeable or passionate about data science or machine learning are welcome to be a member of AI Lab. And for more information about AI Lab research activities as well as the initiative, we invite you to join AI Lab group at the link below. And moreover, you can watch the playlist of AI Lab seminar on this YouTube link. And you can see it in the meeting chat. And right now, I would like to introduce Mr. Cleg Peter Ovil, the speaker of our seminar today. Good afternoon, Peter.
Yes, good afternoon, Lum, and good
Okay,
afternoon, everyone who are here.
so can you say something about yourself and the topic of the seminar to our audience?
Yes. First of all, can you hear me clearly?
Yeah,
Okay.
okay.
My name is Cleg Peter Ovil. I am Haitian, so I am from Haiti. And for those who don't really know where Haiti is located, so it's located in Central America. And I am here as your speaker because I spent 6 months internship at FBT Software, especially in DCS. So where I was working on this subject, tumor detection based on medical images using deep learning. So my motivation today is just because it was a very nice experience for me. So I said, okay, let me participate like this. I could share my knowledge and also learn from you because I know that a lot of you here um, understand what I am going to share with you. So like this, you will ask questions. Maybe I will learn a lot from you. So thanks for joining. I see some people that I know and some people that I don't know.
Okay,
Still,
so
mhm.
let's start your presentation and can you share your slide?
Yes. Mine is so good. Can you see it now?
Yes,
Oh,
let's
okay.
start.
Okay, thank you.
Okay.
Yes. Okay, let's start now. So this is the subject. The title is tumor detection based on medical images using deep learning, but the tumor type is breast cancer. There are many type of tumor, of other like part in the body that they use deep learning for it, but for my subject, it was breast cancer. And during this internship, I was supervised by Mr. Pham Chi Kum and all of the other developers and all the other scientists. So they were here to support me. So in this subject, we have 5 points: the introduction, and then the methodology that we use to resolve this problem, and then our experimentation, and then also the results and discussion that we will have at the end of this webinar. For the introduction, for this subject to be practical, so this is a real problem all over the world. We have women, they are dying because of breast cancer. So because of most of the time, if there was a kind of detection, like early detection, maybe this patient or that woman could, I don't know, try to resolve this problem through surgery, or I don't know, just see the doctor like earlier and then understand what's going on in that breast so that woman can understand exactly if the tumor is a benign one or malignant or what's going on. So if there is a mass or calcification type. So because of that problem, like they don't know what's going on, there is no really good detection. So they don't know what they have, if they have problem or not. So this is the cause of death all around the world. Even if in America, Asia, Africa, we have this problem. And then we have radiologists. They work on it, but sometimes their work are not precise. The work take a lot of time. But now how can we use deep learning to resolve this problem? So our expected result is find a solution to detect tumors through images. And now the methodology that we use. So first of all, we had a data set. So that data set is reachable through that link, so that I share with you. And to really understand that data set, so I got to work on it to understand how many images that I have, ROI, and type of tumors. So in total, I have 3,103 images in total. But in this data set, I have full images and ROI. ROI stands for region of interest. For each full image that I have, now how can I know where is the tumor? The ROI will tell me. For each image, I have maybe one or two or three or four ROI. If in one breast I have two tumors, I have two ROI. If I had three tumors, I had three ROI. So I have in total 3,568 ROI. The reason, because in one breast, I can have many tumors. So I can have 1, 2, 3, 4, 5 tumors. So that's why I have a lot of ROI. And then for in total, so I have 6,671. So total image and ROI. But in tumors, we have different type of tumors. We have calcification type and mass. So what's the difference? For calcification type, this is a bunch of tiny deposit of calcium salts that are too small to be felt but can be detected by imaging. So calcification, so I can say it represents like a bunch of dots. However, for mass tumor, so this is a mass in an area of dense tissue with a shape and edges that make it look different than the rest of the breast tissue. So when you are looking on a mammogram, so you can see the mass is a little bit different from the rest of the breast. So this is the two types of tumors that we have, calcification type and mass type. So we have the numbers here. And the total cases, the total of patients that were participated in that cohort was 1,566. That's why we have 1,566 cases. So we have other numbers here to say that how many calcification images that we have and also how many cases, and the same thing for mass. So in total, for training image, I have 2,458 images, and for test images, I have 645 images. So with this data set, so I got to work and then to bring out a good solution. Now, during this work, I had also abnormal images. When I compare the shape of full mammogram and ROI, ROI should be the same shape as full images, because if I compare them, if the shape If the shapes are not the same, I won't find the right location of that tumor. So for that reason, I got to compare all the images, and then I found out 85 images, so 60 classification type of tumors, and then mass 25. So I got to compare and then to resolve that problem in order to find the right location of the tumor. And the next step was preprocessing. So this is an image of full mammogram. So when you see it, it's not that clear at all. So CNN would be very hard to find where is the tumor. So me myself, I cannot see anything. So for the computer, so I know that it's like a machine problem, but still we got to apply some preprocessing just to make the image clearer. Um, is everything fine so far? Hello?
Yeah.
Is everything fine? Can you hear me?
Yes. Okay.
Okay. Okay. Thank you. And can you see everything?
Yes. It's good.
Okay. Okay. So this is the full mammogram. And then so this is the full mammogram. Now, what I should do next? The next step was to crop images because with the first repository that I was working with, I had a very hard time to input my images because they were too large. So I got to crop images 1024 times 1024. Actually, the shape is not okay because it should be squared. But, when I'm using latex, so the shape is, but normally it should be a square. So it is square, but for my presentation, the shape is, getting crazy. Now, the first thing was to cropping, and then the second work was to apply truncation normalization and also histogram qualification. That work, the real name is Cleg. So I use it through papers that I've read because it's researches first. So I got to read a lot to understand how scientists or researchers find out solutions for this problem. And then this is what I found. And then I apply it, and then it worked. So when I applied this histogram equalization and truncation normalization, so I have this effect. So now it's way clearer, so I can see what exactly in there. And then I process with my work. So I experiment with two architecture with faster RCNN and YOLO. So the first experimentation was with faster. So let's try to understand what faster RCNN does. So this is a family RCNN. I know a lot of you know more about me. So let me just give some fundamental explanation. So first of all, here we have the input image. So when I input the image with the right shape, etc. So here we have two nice work. The first work is anchor boxes generation. It is really important because I cannot detect anything, any object cannot be detected without anchor box. So when faster RCNN generate a bunch of anchor boxes, so in the object, wherever the object is in the image, so I will see where the image, and then so we will process with IOU, etc., to have exactly where that tumor or where that object is. And then we have the very important RPN. This is a small CNN, so it would help to not so after generating anchor boxes, now to know exactly so how the process will do with IOU, etc. So RPN is here for that. And then after we have the ROI sample. So the output here is like it will reshape everything. So all the process that were going on here, or I here will crop everything to have this very same shape. And then we will have the detection. So after the detection, we have another process right here, detection target generator. So it will provide to us the right anchor box, which means that if I have an object output, so I know that, okay, this one is a tumor. Now to have the right anchor box, so right here, after the detection, detector target generator will process the right anchor box. So no matter how large that anchor box could be, or no matter how small it could be too. So in a nutshell, this is what faster RCNN will help me to detect the object. So our object is tumor. So now, when we get our faster RCNN set up, so we got to still work on our data. So we got to understand how will we make distribution for aspect ratio. To understand that in our, so for example, here, this is train average on all data. So when we have all of our data, so we should, so in our pipeline file, we have to clearly set up parameters to cover up all of the size of our bounding boxes through aspect ratio. So we got to get that for train images. So these bars tells us, okay, so in this area, so we will start with 124 and then to continue until 195. So to have like good scale and then good aspect ratio in order to tell faster RCNN, okay, each time that you see this object, so this is how you will define the size of our bounding box. And then we continue with the same process with our evaluation average on all data. So we have train, evaluation, and then test. So we did the same thing to understand each size of tumor. So they should have a specific size of bounding box. So that's why we worked on aspect ratio distribution. And then we continue with some important parameters that we should modify. So in these parameters, so not only aspect ratio, scale, and we have also how many steps. So for my repository, so it was 108,100 steps equals to 100 epochs. And then the way that I split my data, it was 7-to-1, like 70% of all my images. So I got to train. So I have 70% for train, 20% for test, and 10% for evaluation. And then as backbone architecture, I worked with ResNet 50. And then I got to select the best model for evaluation of my model. So I continue with my experiment. So after training, after modify all the important parameters, like I said before, and then the first result that I have was a little catastrophic with faster RCNN and ResNet 50. So on 645 images that I had for tests, so I didn't have a big result because for my class it was tumor, but for the quantity of true positive was 219 over like 1,370. So I had more false positive. So the accuracy was not good at all. So it was not the end. I got to continue working to see how can I find out a good solution. And then I continue. So it was 704 for ground truth. So I have all these details. But in a nutshell, the accuracy that I had was 16%. So which is not good at all for like a good solution. So this was the solution that I have for faster RCNN, which was not good. And I continue with YOLO. I try with the same data set, the same quantity of images, and then the same type of preprocessing. When I try with YOLO, I have another type of result. So that let me think about many things. So that's why we have discussion at the end. So we all can share our point of view. But me, myself, I said that, okay, so this is what I think, and then this is what I should do. Now for YOLO, it works differently. YOLO stands for you only look once. YOLO stands differently. So when you input an image, what YOLO does, it divides that image and then it will output bounding box. The process is simpler and surer. So I tried to use YOLO to see what kind of result that I could have with the same images, same quantity, and then same preprocessing. And when I train my data, so in my graph here, but here I got to say that for YOLO, I train the data separately. I know that I have calcification tumors. I know that I have mass tumors. So I train calcification tumors separately and then mass tumor separately to see what can I have as feedback. And then when I did that, when I experiment with Darknet as a backbone architecture, I only train classification images. When I train classification images, so this is the graph here, so you can see the number. So it's higher compared to faster RCNN, but still it was not good. So here you can see everything clear here. With YOLO, when I train only classification images, I had an accuracy of 57%. So now I have more true positive. It's 152 over like true positive 330, 38, and false positive is 152. So I have more true positive. So this was good. And then I tried to understand something. Okay. And then when I continue with mass images, and then I have a higher accuracy here. For you to see clearer, here I have an accuracy of 81%. So I have 299 images over 805 images. So here I have like a better precision, and then I could make better detection with mass tumors or mass images, because with all mass images, I have tumor as object. So this is what I want to detect. So with this result, I start to really understand why when I train all the images together, so I could not have like a good result. But when I train separately, so I can say that, okay, for mass images, I have good result. Okay, I can work now on classification image itself to see what's going on. And as a result, so this is when I detect calcification tumors. Remember, it's a kind of that like tiny um, deposit of calcium, salt. Okay, so they are really tiny. So that's why here, if you can see, so we have dots here. So in this image, I have two tumors, type of calcification. So they are detected. And then here, this is a mass. This is not calcification. So if you can see here, it's bigger. And then, so I make that detection too. And then we still have other results here. These are calcification, and then this is mass. So mass is bigger. And this is mass too. It's bigger. So after pre-processing, I can see. So even with with your eyes, you can see where that tumor is. So now as discussion, I said, I realized that I had like an unexpected result with faster RCNN. I should have an adapted preprocessing for calcification images. Definitely. If with that preprocessing that I have, I could have good result for mass images. Obviously, for calcification, if I don't have good result, I have to see that preprocessing, maybe to read more papers to understand if there is no another way to apply a better preprocessing. And then I could still see like anchor box distribution, aspect ratio distribution, and then other parameters to modify. And the problem that I noticed when we are working on deep learning, we have repository that we use. Sometimes some repository can good for this type of images, but it's not that good for medical images. I think the repository that I used for faster RCNN, maybe it was not like the better one. I can still try to understand this. And then lack of precise documentation to find out the best solution. So this work that I've realized, maybe when I'm explaining it, so it looks like a simple thing, but to me it was very huge because I didn't have all the solutions before. So I got to read a lot. I got to search on the net and then read a lot of papers to at least understand what should I do. And also the repository that I got to use, a lot of bugs and then a lot of, you know, library to install and then errors. So I got to figure them out. So it took me much time to realize at least, okay, what to do. Even if the work is not perfect yet, but this is how, if we could have a very good solution for both classification images and mass images, so we can propose that solution to any hospital or very like big center for healthcare. This could be a very nice solution to help radiologists, not to replace them, but to help them to make the work faster and more accurate. So in a nutshell, this was my presentation on that subject, tumor detection based on medical images using deep learning. So deep learning can help a lot in healthcare. Now, for those who have questions, for those who have like, I don't know, something to say, I think this is the best moment for you to ask the question, or I don't know, to comment or to say anything related to that subject. Thank you.
Okay, so thank you, Peter, very much for your dedicated presentations. And now it's the time for questions and answer. And our audience, you can turn on your audio or write the questions in the meeting chat.
Hi, hello, Peter. Can you hear me?
Yes, I can hear you, sir.
Hi, thank you very much for that presentation, man. Let me ask you something. So I understand that you need more information, a little more scientific paper to read to get more accuracy in your algorithm, or do you think that you have enough resource to increase? You only need more image to compare.
Can you can you say that again, please? The last part of your question.
Okay. Do you think that to improve the accuracy that you are getting now 81, right? So
Yes.
do you think that you need more image to make the training, or do you think that you need get more information about the current state of this kind of solution?
Okay. Thank you for your question, sir. I don't think I need more images because with the quantity of images that I have, I already have a good solution somehow. However, for classification images, maybe um, the the methodology that I use is not enough. So I got to make more researches first, and also to understand um, what kind of repository could help me better with especially faster RCNN because the result that I have is not high enough.
Okay, thank you.
Pete, we received some questions in the meeting chat, and you can scroll down to read it. Okay. The first question from Mr. Phạm Văn Hùng. He asks you how many images did you use as training data for the model?
Okay, thank you. It took me 48 hours to train data over 100 epochs. So 48 hours, so around 48 hours.
Okay, so it is the answer for the second question. And the first question is how many images did you use as training data for the model?
How many images did you use as training?
Yeah.
Okay. It's 2,438 images.
Can you write the number?
Yes.
Okay.
First of all, let me. Here, can you see? So
Yes.
if you can see here, like in total, all images that I have for training is 2,458. I'm sorry. And then 645 images as training.
Okay, I can see it. And Mr. Fong, he asked you, how did you choose train width to use prediction?
Okay. Thank you for your question. Oh, Mr. Lighteful. And first of all, before answering, I have to say thank you to Mr. Foam because he was really helpful during that internship for me. Now, how did I choose? How did I choose trained? I'm sorry. How did I use? How did I choose train weight to use prediction? For faster RCNN after training, I have the frozen frozen.pb, so that I use it first of all to have detection result, and then I have ground truth, and then I have another repository to use to calculate MAP. So after training 48 hours, so um, that frozen file that I have, so this is the one that I use, Mr. Foam, to make the prediction. Because this is by it, I can have detection result. So if I can have detection result and then I have ground truth, so with that repository, so this is the two things that I need to make prediction: detection result and ground truth. So this is like this that I use. This is how I can make prediction with faster RCNN. Now with YOLO, after training, in my backup file, I have all the model of the models. So I have the best model, I have different ones. So I got to use one by one to see what is the best accuracy that I can have. Most of the time, the best model, it is written somewhere like in the backup. They indicate you, okay, this is the best model. And then when I test with the best model, I usually find the best result. For example, like mass images, when I let me show you. Yeah. For example, here, my repository, there is a space that tell me, okay, to calculate MAP. Now, to calculate my MAP, I use my best model that I already have on my Google Drive because I use Google Colab to train. So on my backup file, so I can use the best model, and then it predicts me 81%. So this is how I make my prediction. I don't know if I'm clear enough, Mr. Fong.
Okay, the question from Mr. Biet Thành Trí.
Okay, give me 1 second to read it. Okay, Mr. Tang Chi. I think this is the same question with Mr. Fong. Actually, yes, you're right. Um, First of all, when I'm training my data, the senior developer, Mr. Tien, helped me to figure this out. I buy on Google Colab 2 TB of space. And then when I'm training with faster RCNN, all my metadata, all my files, they are saved in a specific in my specific storage. Okay, so this is the first thing. And then on the repository also, there is a folder named save model. So in that save model, there is a file named inference frozen.pb. So that inference.pb, this is the most important file that I need. If I don't have it, I can still convert my metadata. I think it's 3. So when you combine them together, you can still have the .pb with the same version of TensorFlow that you were training your data before. So thankfully, I had my in frozen graph.pb. So when I downloaded, it took me a little time to download it from my Google Drive to locally. After having this, it is easy for me to determine my detection result because the repository that I use, I need two information. I need different files for detection result. So after training, okay, what were the results? So in frozen graph.pb can help me to find this out. And then the second information is the ground truth. Okay, so how can I calculate this? So it's very easy. It's by my XML file. So it's very easy. I already have them. I can find out my ground truth. So with these two information, I can calculate my MAP. So this is how I process to calculate to evaluate my model. And then with YOLO, like I told you, it's easier for me to do it because they already like classify everything. Still on my storage backup, which is 2 TB, I can easily see which is the best model because it's written somewhere, okay, with they told me, okay, this is the best model. So I can still use, like, if I use my curiosity, so I can use different file before using the best model, just to see if really the best model is gives me better accuracy. But at the end of the day, I always find that the best model gives me the like a better accuracy. So in a nutshell, this is how I can explain to you. I don't know if I'm clear enough, Mr. Tang Chi.
Okay, thank you. Okay, so maybe Mr. Nguyễn Thành Trí questions is the last question of the seminar today. And yeah, thank you everyone very much for your time today. And we hope that you have learned something interesting from the seminar. And we look forward to your participations in the next seminar of AI Lab. And thank you, Pete, very much for your dedicated presentations today. And yeah, thank you and goodbye, everyone.
Thank you. Thank you, everyone.